Good afternoon. HOD Professor A.K. Chaturvedi sir, my seminar guide Pradesh Tripathi sir, seminar coordinator Rajan Giri sir, faculty members, examiners, and my friends. I am MOHIT GOYAL, pursuing my BTech from University Departments of Mechanical Engineering in Rajasthan Technical University, Kota. Today, I am pleased to be here in front of you to deliver the presentation on the topic of CFD analysis of ventilation in a hospital room. Let's start with an introduction. CFD analysis, short for computational fluid dynamics analysis, is a powerful tool used to study airflow and thermal behavior in various environments, including hospital rooms. The objective of this presentation is to explore how CFD analysis can be applied to evaluate and optimize ventilation systems in hospital rooms, aiming to improve indoor quality and enhance the safety of patients and healthcare workers. As we all know, maintaining a healthy and safe environment in hospitals is of paramount importance. Adequate ventilation plays a crucial role in ensuring good indoor air quality, reducing the air risk of airborne infections, and providing a comfortable environment for both patients and healthcare workers. CFD is a computational tool used to simulate airflow patterns and thermal behavior in a complex environment like hospital rooms. It provides a detailed investigation of airflow velocities, temperature distribution, and pollutant dispersion. By optimizing ventilation parameters through CFD analysis, efficient and effective ventilation systems can be designed to improve air quality and ensure safety in hospitals. Now, we will delve into the CFD analysis process and understand how it can help us evaluate and enhance ventilation system in hospital rooms. To start, let's take a look at the CFD simulation process. CFD simulation involves several key steps. Geometry creation. A digital model of a hospital room is constructed, including walls, windows, doors, and ventilation openings. This model accurately represents the physical layout of the room to simulate real world conditions. Mesh generation. The model is divided into small computational cells, creating a mesh that serves as a foundation for solving fluid flow equations. This mesh allows us to capture the intricate details of airflow and temperature distribution within the room. Boundary conditions. We specify the airflow rates, temperatures, and pressure at the boundaries of the hospital room to replicate realistic scenarios. This include the configuration and placement of supply and exhaust vents, which significantly impact the ventilation performance. Solver settings. We select appropriate turbulence models and numerical methods to accurately represent the airflow behavior within the hospital room. These models help us understand how air moves, mixes, and distributes within the space. Post processing. Once the simulation is completed, we analyze the results and generate visualizations to gain insights into the airflow patterns, temperature distribution, and air quality within the hospital room. This information forms the basis for making informed decisions to optimize the ventilation systems. Now let's talk about the input parameters for CFD analysis. To conduct accurate analysis, we consider various factors including room dimension and geometry, ventilation system configuration, HVAC settings, thermal loads, occupancy conditions, and external conditions. By simulating different scenarios and optimizing these parameters, we can gain valuable insights into the effectiveness of the ventilation system and identifying areas for improvement. Moving on to the CFD analysis result and interpretation. Airflow patterns. Streamlines and velocity factors help us understand the direction and intensity of airflow within the room. We can identify areas of stagnant air or inadequate air circulation. Temperature distribution. Color counter plots allow us the temperature distribution across different zones of the hospital room. This allows us to identify areas with temperature variations that may impact patient comfort and healthcare workers' productivity. Contaminant concentration. By analyzing the dispersion of pollutants or contaminants, we can assess the effectiveness of the ventilation system in removing them. This is crucial for reducing the risk of airborne infection. Particle dispersion analysis. We can evaluate the movement and transport of airborne particles, including pathogens. This helps us identify potential exposure areas and design appropriate control measures. Ventilation effectiveness. Through these analyses, we can determine the effectiveness of ventilation systems and identify the potential areas for optimization. This may involve adjusting vent positions, airflow rates, or implementing other solutions. Now let's talk about a case study. Problem. The initial problem was the presence of inadequate ventilation in the ICU, leading to suboptimal air quality and concerns about infection control. This prompted the need for a thorough assessment and optimization of ventilation system. Simulation setup. The first step in the CFD analysis was to create a digital model of the ICU room incorporating accurate measurements and specification. This 3D model includes walls, windows, doors and ventilation openings to replicate the actual environment. Mesh generation. The model was then divided into small computational cells using appropriate meshing techniques. This step allowed for accurate simulation of fluid flow dynamics and capturing of detailed airflow patterns. Boundary conditions. Next, the airflow rates, temperature, and pressure in the inlet and outlet vents were defined based on the actual ventilation system setup in the ICU. This ensures that the simulation represented in the is in the real world condition accurately. Solver settings. To accurately capture the complex airflow behavior within the ICU, a validated turbulence model and numerical method are selected. These choices enable the simulation to accurately predict airflow patterns and interaction within the space. Post processing and analysis findings. Once the simulation was completed, the results were analyzed to evaluate airflow patterns, temperature distribution, and airflow quality metrics within the ICU. The CFD analysis provides several valuable insights and findings. Airflow patterns. The analysis revealed areas of stagnant air and insufficient air exchange near certain patient beds. Additionally, localized recirculation zones were identified indicating ineffective ventilation in specific regions of ICU. Temperature distribution. The simulation also highlighted temperature variation across different zones of the ICU. This variation indicated the need of better temperature control to ensure thermal comfort for patients and healthcare staff. Air quality assessment. The analysis allowed for the evaluation of contaminant dispersion and potential airborne pathogen transmission within the ICU. The assessment helped identify areas where the filtration and circulation needed improvement to maintain a safe environment. An intensive care unit ICU in a hospital room was experiencing inadequate ventilation, resulting in suboptimal air quality and concerns about the potential for airborne transmission of infections. The existing ventilation system configuration and airflow patterns needed to be assessed and optimized to ensure the safety and well being of patients and healthcare. In conclusion, the application of CFD analysis in optimizing ventilation systems in hospital rooms is a powerful tool that can significantly enhance air quality, infection control, and thermal comfort. By leveraging the capabilities of CFD, hospitals can make evidence based decisions to optimize their ventilation systems, ultimately benefiting the health and well being of patients and healthcare workers. Thank you. मेरे को चश्मा लगाना पड़ेगा